Titration reactions form a very important class of acid-base reactions, and the word titration implies the increase in one reactant that overtakes the other reactant to become the reactant in excess. But in acid-base reactions, there are two other aspects that we want to focus on. The first is that across the international spectrum of chemical analyses, titration reactions are the way in which a pH of an unknown solution is determined by the addition, for example, of small amounts of a base to an acid. But more than that, in the analysis of acid-base reactions, the landscape of pH against the volume of the added species turns out to be extremely illustrative of the reaction processes that take place in acid-base reactions. So we want to focus on titration reactions. We want to add a base to an acid solution. And so a titration plot always has the same characteristics. It plots the pH on the vertical axis against the volume of the added reactant. In this case, we're adding a base to an acid. And so this landscape of how the pH changes as a function of the added base constitutes the titration plot. So we add a base to an acid solution, and then we examine carefully how the pH responds. And as we'll see, when we analyze this behavior of the pH against the added base in this example, it tells us a great deal about how the acid and base interact. And in our case of adding a base to an acid, we want to determine the pH of that mixture, and we will see exactly how we do that. But more than that, we want to watch carefully the interaction of the acid and the base, because it tells us a great deal about the dynamic of this interaction. So we start this analysis of titration reactions by looking at what happens when we add a strong acid and a strong base together. And in this case, we're going to start out with an acid, a strong acid, and we're going to add the base to that acid. So the strong solution starts out with a pH that's determined by the molar concentration of the strong acid in solution. So our initial condition then is a calculation of the pH of that acid solution before we've added any base to it. So suppose we start with a 100 milliliter solution of hydrochloric acid that's a 1/10 molar in acid concentration. To this mix, we're going to add small increments of sodium hydroxide. And sodium hydroxide, when it's added to water, as we know, forms a sodium cation that does not interact in any way with the acid. But the other product, OH minus, the hydroxide anion, reacts extremely strongly with the acid. And we know that because the reaction of the hydroxide anion with any acid is driven by a strong release of Gibbs free energy, driving that reaction forward to completion. So we're going to add these small increments of sodium hydroxide, and we're going to map out the pH as a function of that added NaOH. And we're going to recognize that the OH minus that comes out of the dissociation of sodium hydroxide is going to react releasing Gibbs free energy with H3O plus to form water. And that reaction of OH with H3O plus is so potent in its release of Gibbs free energy that that reaction goes to completion. So we set up a situation where anytime we put OH minus into an acid solution, every single one of those OH minus species attacks an H3O plus and annihilates it along with itself to form pure water. And this is a characteristic that resides throughout all acid-base reactions, and particularly with titration reactions. So the titration curve then begins with its initial condition in the acid with a pH calculated directly from the concentration of H3O plus. And as we said before, the H3O plus concentration is equal to 0.1 molar. Well, that means that we can simply calculate the pH by taking minus log to the base 10 of that concentration. So minus log to the base 10 of a 10th molar is exactly 1. So we start out with a pH of 1 before we've added any base to this combination. So the next step is when we add that OH minus to the H3O plus, the key thing is that we recognize that the OH minus added is equal to the H3O plus originally when we reach the equivalence point. And that's what makes the addition of a strong acid to a strong base particularly simple, because there's the annihilation of each H3O plus by each OH minus that's added. So at the point where we've reached this equality, where the added OH minus from the base is equal to the original H3O plus, though the reaction that's driven by the release of free energy, namely H3O plus plus OH minus going to 2H2O, means that every single one of those original H3O plus cations that was in solution is annihilated one by the addition of the OH minus. And so we work our way along this plot, slowly working our way toward the equivalence point. And at the equivalence point, we have the fact that this original H3O plus is exactly equal to the added OH minus. Well, that means that every single one of the H3O plus that was originally there, by virtue of its reaction with OH minus, has disappeared into the background water solution. And that means that we come back to the simple autoionization of water. And we know exactly how to calculate that. Pure water has a pH equal to minus log to the base 10 of 10 to the minus 7, which is equal identically to 7. And that means that the pH at the equivalence point is driven by the autoionization of water. There's no buffering, no hydrolysis, no partial dissociation of acid and base. It's simply a function of the autoionization of water.